Bitcoin, a peer-to-peer electronic cash system by Satoshi Nakamoto introduction commerce on the internet, has come to rely almost exclusively on financial institutions serving as trusted third parties to process electronic payments. While the system works well enough for most transactions, it suffers from the inherent weaknesses of a trust-based model. In this model, completely non-reversible transactions are not actually possible, since financial institutions cannot avoid mediating disputes. This mediation increases transaction costs, which limits the minimum practical transaction size and prevents the possibility of small, casual payments. There is also a broader cost, the loss of the ability to make non-reversible payments for non-reversible services. Because a payment can be reversed, the need for trust spreads. Merchants must be wary of their customers, demanding more personal information than would otherwise be necessary. A certain percentage of fraud is simply accepted as unavoidable. These costs and uncertainties can be avoided in person by using physical currency, but until now, no mechanism has existed to make payments over a communication channel without a trusted party. What is needed is an electronic payment system based on cryptographic proof instead of trust, allowing any two willing parties to transact directly with each other without the need for a third-party intermediary. Transactions that are computationally impractical to reverse would protect sellers from fraud, and routine escrow mechanisms could easily be implemented to protect buyers. In this paper, we propose a solution to the double spending problem using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. The system is secure as long as honest nodes collectively control more processing power than any cooperating group of attacker nodes. The electronic coin, we define an electronic coin as a chain of digital signatures. Each owner transfers the coin to the next by digitally signing a hash of the previous transaction and the public key of the next owner, adding these to the end of the coin. A payee can verify these signatures to confirm the chain of ownership. The problem, of course, is that the payee cannot verify that one of the previous owners did not double spend the coin, meaning signing it over to someone else earlier in time. The traditional solution is to introduce a trusted central authority, or mint, that checks every transaction. After each transaction, the coin must be returned to the mint to issue a new coin, and only coins issued directly from the mint are trusted. The problem with this solution is that the fate of the entire money system depends on the company running the mint. To accomplish this without a trusted party, transactions must be publicly announced. We need a system for participants to agree on a single history of the order in which transactions were received. The payee needs proof that, at the time of each transaction, the majority of the network agreed it was the first one received. The timestamp server and proof of work, the solution begins with a timestamp server. It works by taking a hash of a block of items and widely publishing that hash. The timestamp proves that the data must have existed at that time in order to get into the hash. Each timestamp includes the previous timestamp in its hash, forming a chain, with each additional timestamp reinforcing the ones before it. To implement this on a peer-to-peer basis, we use a proof-of-work system. This involves searching for a specific value that, when hashed, begins with a required number of 0 bits. This is a difficult, resource-intensive process, but once the work is done, it can be verified by anyone with a single calculation. For our network, we implement proof of work by incrementing a nonce, a random number, in the block, until a value is found that gives the block's hash the required number of 0 bits. Once the CPU effort has been expended to satisfy the proof of work, the block cannot be changed without redoing the work. Furthermore, as later blocks are chained after it, the work required to change a single block would include redoing every subsequent block in the chain. Proof of work also solves the problem of majority decision-making. If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IP addresses. Proof of work is essentially one CPU, one vote. The majority decision is represented by the longest chain, which has the greatest proof-of-work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. To modify a passed block, an attacker would have to redo the work of that block and all blocks after it, and then catch up with and surpass the work of the honest nodes. As we will see, the probability of a slower attacker catching up diminishes exponentially as more blocks are added. The steps to run the network are as follows. New transactions are broadcast to all nodes. Each node collects new transactions into a block. Each node works on finding a difficult proof of work for its block. When a node finds a proof of work, it broadcasts the block to all nodes. Nodes accept the block only if all transactions in it are valid and not already spent. Nodes express their acceptance of the block by working on creating the next block in the chain, using the hash of the accepted block as the previous hash. Nodes always consider the longest chain to be the correct one and will keep working on extending it. If two nodes broadcast different versions of the next block simultaneously, some nodes may receive one before the other. In that case, they work on the first one they received, but save the other branch in case it becomes longer. The tie is broken when the next proof of work is found and one branch becomes longer. The nodes then switch to the longer one. Incentives and sustainability. By convention, the first transaction in a block is a special transaction that starts a new coin owned by the creator of the block. This adds an incentive for nodes to support the network and provides a way to initially distribute coins into circulation, as there is no central authority to issue them. This steady addition of new coins is analogous to gold miners expending resources to add gold to circulation. In our case, it is CPU time and electricity that are expended. The incentive can also be funded with transaction fees. If the output value of a transaction is less than its input value, the difference is a transaction fee. Once a predetermined number of coins have entered circulation, the incentive can transition entirely to transaction fees, making the system completely inflation-free. This incentive encourages nodes to stay honest. If a greedy attacker were able to assemble more CPU power than all the honest nodes combined, he would have to choose between using it to defraud people by stealing back his payments, or using it to generate new coins. He should find it more profitable to play by the rules, which favor him with more new coins than everyone else combined then, to undermine the system and the validity of his own wealth. Reclaiming space and privacy. Once the latest transaction in a coin is buried under enough blocks, the spent transactions before it can be discarded to save disk space. We use a data structure called a Merkle tree to allow this without breaking the block's hash. This allows the network to stay manageable in size. Even if the network grows significantly, the headers of the blocks remain small enough to fit in a computer's memory. Regarding privacy, the traditional banking model achieves privacy by limiting access to information to the parties involved and the bank. Because the Bitcoin model requires all transactions to be public, privacy is maintained by keeping public keys anonymous. The public can see that someone is sending an amount to someone else, but without information linking the transaction to a specific person. As an additional firewall, a new key pair should be used for each transaction to keep them from being linked to a common owner. Security and calculations. We have considered the scenario of an attacker trying to generate an alternate chain faster than the honest chain. Even if this is accomplished, it does not open the system to arbitrary changes. Nodes will not accept an invalid transaction as payment, and honest nodes will never accept a block containing them. An attacker can only try to change one of his own transactions to take back money he recently spent. The race between the honest chain and an attacker chain can be described as a binomial random walk. The probability of an attacker catching up from a deficit drops exponentially as the number of blocks the attacker has to catch up with increases. With the odds against him, if the attacker does not make a lucky lunge forward early on, his chances become vanishingly small as he falls further behind. For a recipient to be certain a transaction is secure, they simply need to wait for a few blocks to be linked after their transaction. This makes the probability of an attacker catching up mathematically negligible. Conclusion: we have proposed a system for electronic transactions without relying on trust. We started with the framework of coins made from digital signatures, which provides strong control of ownership but is incomplete without a way to prevent double spending. To solve this, we proposed a peer-to-peer network using proof of work to record a public history of transactions. This history quickly becomes computationally impractical for an attacker to change if honest nodes control a majority of CPU power. The network is robust in its simplicity. Nodes work all at once with little coordination. They do not need to be identified, as messages are only delivered on a best effort basis. Nodes can leave and rejoin the network at will, accepting the proof of work chain as proof of what happened while they were gone. They vote with their CPU power, expressing their acceptance of valid blocks by working on extending them and rejecting invalid blocks by refusing to work on them. Any needed rules and incentives can be enforced through this decentralized consensus mechanism.